All right, folks, we have, okay, let's begin. This is the first of two lectures on hidden Markov models. We have 12 people in class, 10 people. All right. HMMs and Kalman filters. Kalman filters are probably the most popular technique still used in controls and for tracking and prediction. And HMMs can be thought of as a precursor. So we'll be spending the next two lectures talking about HMMs not merely as a topic by itself, but also as something that sets us up for understanding Kalman filters. So let me begin with this simple problem. This is a common problem that used to end up in many interviews in the past. So there's a room of this kind, which is a cube, perfect cube. Every edge is 1 unit long, and there's a spider and a fly as shown in the picture. Now the fly is going to be seated in just wherever it is. The spider takes 1 minute to go. The spider only walks along the edges of the wall, and it doesn't walk along the surface. And it takes 1 minute to go from any corner to any corner, any adjacent corner. And when it arrives at any corner, it randomly selects one of the 3 edges going out of the corner for its next path. So given that the spider takes 1 minute to go from one corner to the other, what is the life expectancy of the fly? Has anybody encountered this question, and how would you go about solving it? Anyone?
Yeah, so we would need to calculate the expected number of steps it would take for a spider to reach the fly.
Yeah. And how would you do that?
We
It's a
could
perfectly
recursively look at the expected number and the adjacent steps and add one to that.
And how deep would that recursion go?
Um,
It will be exponential, I think.
It will be exponential. Yeah, that's a good answer. But does anybody have a simpler answer to this? Anyone? So, okay, I won't spend too much time on this. It's a very simple problem, actually. Now, there's something very special about the manner in which I set up the problem. This is a common enough problem that whenever the spider arrives at any corner, it follows any one of the 3 edges going out of the corner with equal probability without actually bothering about how it got to that corner. So where it's going to go from any corner only depends on the corner that it's at. Are you familiar with the kind of process that is? What kind of process would
Markov process?
That's a Markov process. In fact, this cube over here, it has 8 corners. It's a Markov chain. Again, what do we mean by a Markov chain? Anyone? Has anybody encountered the term Markov chain?
Is it a finite state space where the transition between each state is Markov process?
So a Markov chain is typically a finite state system. So in this case, there are 1, 2, 3, 4, 5, 6, 7, 8 states. And when the process is in any particular state, then the future only depends on which state it is at. It doesn't depend on how it got to that state. So from any state over here, for instance, it has 1/3 probability of going to each of these adjacent corners, right? So it's a Markov chain. We'll see more of Markov chains. And if you're interested in finding out how this particular problem is solved, post on Piazza. It's a 3-line solution. Anyway, so the kind of problems you're going to be looking at are problems of prediction, like physical trajectories. if you want to track the movement of automobiles or rockets or heavenly bodies, or if you want to predict natural phenomena, or if you want to predict financial data in a stock market, or world affairs, who's going to win the next election signals. All of these are about predicting time series. We've already seen some instances of predicting time series. Now, before that, we've seen this problem in earlier lectures. Anybody remember this? This must have come up in an earlier lecture. Which one?
Time series prediction.
Time series prediction? No? Okay. So this should...
CCA, canonical correlation around.
It was presented, you saw this example in the CCA class, right? And those of you who haven't seen this before obviously didn't attend the class. Anyway, so here was the problem. How did we set up the problem? You remember? Guys, at least some of you were in the class. So how did we set up the problem? What was the problem?
We were trying to predict the offset of the location where the arrow would land based on the wind speed.
Okay, so something like that. Actually, it's a slightly different problem. Okay, so imagine this is how, if I remember the slides right, this is how I'd set it up. Imagine that you want to measure wind velocity, right? But you don't have, the only tools that you have with you are a bow with a bunch of arrows and a target of this kind, right? So what would happen? You could shoot an arrow, and if the arrow, if your aim was perfect and you shot directly at the bullseye, if there were no wind, and assume there's no gravity, what would happen to the arrow? If your aim was perfect, what would you hit?
It will hit the target, the center.
It will hit the bullseye, right? Now, if there's some wind, what will happen? What happens to the arrow if there's some wind?
It sways
still
and misses the bullseye.
It sways and misses the bullseye. How much will it sway and miss the bullseye by?
That will be proportional to the wind velocity.
It will be proportional to the wind velocity and the time taken for the arrow to hit the bullseye, correct?
Yeah.
You guys, right? So here's what. The arrow position at any time, in the absence of anyone, it's going to, if everything were perfect, it's going to hit bullseye. But if you shoot the arrow, then you're going to drift a little bit, and how much you drift by depends on the wind velocity, right? It's going to be some a times the velocity, where the velocity is a vector, and a quantifies the time it takes for the arrow to go from your bow to the target, plus some noise, because you're not a perfect shooter, right? So this second equation actually relates the wind velocity to how much you're going to miss the bullseye by. Does this make sense? Guys? Okay, if it made sense, give me a thumbs up. Yes.
Yes.
Okay, I'd like to see at least a yes on the chat. So, I know that you guys are not falling asleep on me, right? So now, if I just shot the arrow, would I be able to determine the wind velocity from the position of the arrow? Yes or no?
We would need the time as well.
Yeah, so I'm assuming that you know this A, right? You know this matrix A. Then what happened to my mouse? Okay. If I know this matrix A, would I be able to recover S?
Yeah. Yeah.
Are you sure? So the wind velocity is three-dimensional, the offset is two-dimensional, right? So, but let's assume that, they're all the same dimensions. Then within this uncertainty gamma, you can sort of guess the wind velocity based on the position of the arrow. But then, yes, the wind velocity is not constant. It keeps changing with time, right? So the wind velocity at any time t is going to be, if you're constantly shooting arrows at a regular rate, the wind velocity at any time t is going to be more or less the same as the velocity at the time t minus 1, and it would have changed by some value epsilon t, correct? And so let's say you keep shooting arrows and you make a sequence of observations y1 through yt. So given this sequence of observations y1 through yt, and this, and knowing these equations, can we actually guess the current wind velocity, number one? And based on these, can I predict where the next arrow will go? These are the two questions we're looking at, right? Does the setup make sense?
So y1, y2, yt, are these the position of a single arrow at different times, or the
You're shooting multiple
offsets
arrows.
Okay.
So you're shooting several arrows, right? Each arrow is going to be affected by its current wind velocity, right? But then if I just take a single measurement, I'm going to make some error in estimating the wind velocity. If I consider the entire sequence of measurements, then you know that the wind velocity at any time is very close to the wind velocity at the previous time, correct?
Yeah.
So by looking at a sequence, you expect to get a more accurate estimate of the current wind velocity than if you took just a single measurement, right?
Yeah.
Does that make sense to all of you? Yes or no? There's a single yes. What about the rest of you guys? Because this is the simplest thing I'm going to talk about right now, right? I'll wait for you guys to give me a yes, okay? And so you can see that this is the kind of problem where something interesting is happening. It's a series data with trends. This trend of arrows, so let's say the wind velocity is constantly increasing, then this epsilon would have a positive trend. Or if the wind velocity is just fluctuating around some constant value, then this would be some zero mean value. Regardless, from the sequence of observations, you can even get an idea of what the wind velocity is and how it is trending. So this is a series data with trends. It's a stochastic function of stochastic functions What do I mean by this? The wind velocity itself is not constant. It is constantly changing, as seen by this. So the wind velocity is random, right? And the offset of any arrow is also influenced by this gamma term, which is your own inaccuracy. So even if you knew the current wind velocity, the position yt is also random. And the randomness is this gamma, right? So the current arrow position y is a random function of st. It's a random function because even if you knew the wind velocity, you can never predict the exact arrow position because of this gamma term, which is how inaccurate you are. So y is a random function of st, but st itself is a random time series. So you have one random function, s, and a second variable y, which is a random function of a random function. Does that make sense? Did the two levels make sense here, guys? Okay, so these are what are called stochastic functions of stochastic functions. You had the first variable a, which was the wind velocity, it's stochastic. And then you had the arrow position, which was a random function of the wind speed. So it's doubly stochastic, right? And this kind of situation occurs not just in our silly toy problem, but in many places. Like if you're in a vehicle, right? The current position of the vehicle can be thought of as a random variable. Or in a stock market, the current sentiment in the stock market can be viewed as a random variable. What you will observe is not, when you take measurements, just as over here, you didn't actually see the wind velocity. The measurements you got were the arrow positions, right? So what you will observe are going to be functions of this underlying process, like the arrow position or things you see from the vehicle or the current stock prices of various stocks. Now, the current stock prices are random functions of the current sentiment, which is a random function itself. So all of these are stochastic functions of stochastic functions. And so our problem is to make predictions. So if you're an agent, if you're a sensible agent, here's what you would do. You'd first learn about the process, and you can only learn about the process from what you have observed. So in our wind example, you'd have to learn two things about the process. First, you would need to know the wind speed, learn the wind speed function, and then you'd need to learn the arrow to wind function. So you're going to need to learn the parameters of this function, which tells you how the wind speed changes with time, and the statistical parameters of the second function, which tells you how the measurement can fluctuate even given current wind speed, right? So in the more generic setting, you're going to learn about both levels of the process, and then you want to track the underlying process. In our case, you want to track the wind speed, because that's the real interesting problem. And then if you want to predict future values, you can't just predict future values based on the current observations. The future values are dependent on not the sequence of observations, but on the wind speed, right? And so based on what you've learned about the underlying process, you can now predict the wind speed at the next time instant. And having predicted the wind speed at the next time instant, you can predict where the arrow is going to fall at the next time instant. So that's a two-step process. Does that make sense? Yes, no. Right, that's a single yes. What about the rest of you? Okay, I'll wait, okay? And a specific case of this is what is called a doubly stochastic process, where you have one random process which generates a state variable x, and a second random process whose probability distribution itself is a function of this state variable x. So it's a doubly stochastic process. And the process, you can have an actual doubly stochastic process, or you can have a doubly stochastic process model. What I mean by this is that you see some natural phenomenon, you have no idea how it was produced, but then you can come up with a mathematical model, hypothesize that this was generated by a doubly stochastic process. And then having come up with this hypothesis, you put math to it, this becomes a doubly stochastic process model. And in this kind of setting, the first level variable, which was the wind in our example, could be a quantifiable variable, like the position of a vehicle or an actual wind velocity, right? And the second level variable would be a random function of this first quantifiable variable, like what you observe from the car or the radar measurements you take are a stochastic function of the position. So in this setting, x has some physical meaning. In a different setting, x may not have a physical meaning. For example, x could be the sentiment of the stock market. What is the sentiment of the stock market? It's not a quantifiable thing. You can't attach a number to it, right? And yet, y is a function of this sentiment. And so you have a stochastic function of a stochastic function, stochastic function of a stochastic variable, where the first variable itself is abstract. And the specific kind of process we're going to be talking about, hidden Markov models, are one instance of this, where you have a doubly stochastic process, where the first random process in this chain is abstract. Specifically, the first random process that we look at is going to be a Markov chain. A Markov chain is a process that can go through a number of states, like a random, there are many examples of these random walks, Brownian motion. But in all of these, the characteristic is that there are a countable number of states, and then from any state at any time, the process can go to any other state, including itself, with a probability that depends only on the state that it is in. And the process is going to keep continuing through this unless there's some stopping criterion, typically what is called an absorbing wall. An absorbing wall is a state where you can think of this like the spider which keeps walking around, but then when it hits this wall, it just sticks. It doesn't move from there. So this is a Markov chain. And a stochastic function of a Markov chain is one where you have a second level random variable, which is a function of the first level variable. The first level variable is assumed to be the output of a Markov chain. So this is the state of the Markov chain. And the second level variable is a probability distribution whose parameters depend on the state. So this entire model is called a hidden Markov model because the underlying process is Markov. What you will observe are the y's, which are stochastic functions of the Markov chain. And there's also a second, an alternate name for it. Is called, these are hidden Markov models, but originally these were called stochastic functions of Markov chains or stochastic functions of Markov processes. So that's just a high-level abstraction, a concept of what we're going to be talking about. Hidden Markov models are stochastic functions of Markov chains. There's an underlying Markov chain which generates a sequence of states, and you get a sequence of observations where each observation is at any time, the process is in one of the states, and the observation is a random function of the state itself, right? So here's your first poem. Okay, guys, out of time. Does anybody want to give me the answer to the first question? True or false?
True.
What about the rest of you? True or false? Second one. What about the second question? Also true. Perfect, right? So you get the idea. A doubly stochastic process generates a state variable first and then an observation variable as a function of the state variable. The state variable may be quantifiable or it may not have any quantifiable meaning. It could be abstract. So, changing gears a bit, okay? Well, let me tell you a little story. You've been kidnapped, okay? And you're blindfolded. And because of this, you can only hear the car. Now, these kidnappers are mean guys. They blindfold you. They take you off in the car. And they take you to some far-off place and leave you there. And you must find your way back home from wherever they drop you off. Now, what is your problem over here? Since you're blindfolded, the only thing you can do is hear. So you must determine automatically by only listening to the running automobile, if it's idling, if it's traveling with a constant velocity, if it's accelerating or decelerating. So based on the sounds that the car makes, you have to decide on which of these four conditions it is in, whether it's idling, traveling at constant velocity, accelerating, or decelerating. And now in this problem, you're super acoustically sensitive, and you can determine the sound pressure level of the sounds that you hear, and you can measure it once per second. So here's what you know. Okay, based on this, if I were to give you this problem, how would you solve it? If you are this person in the car Any suggestions on how you could use this to find your way back home? Anybody? Ketan, do you have any ideas?
Not that I can think of right now.
Anybody else?
Could you like try to remember how long you did each thing for a period of time and try to recreate that in the opposite direction somehow?
That's basically what you would be doing, correct? So exactly, you'd want to figure your way back. So, and here's what you know. These are an automobile that's at rest can accelerate or continue to stay at rest, right? An accelerating automobile. Now, an automobile that's accelerating can either hit steady state or continue to accelerate. Or you could hit the brake and begin decelerating. If you're currently decelerating, you can continue to decelerate, or you could come to a complete rest, or you could take your foot off the brake and cruise and travel at steady state, or you could hit the accelerator and accelerate. And if you're traveling at steady state, you can stay in the steady state, accelerate, or decelerate. Let me draw a figure for this, right? That's something like this. So if the car is currently idling, then you can't suddenly go to a cruising state when you're idling. You must first accelerate to it. So if you're idling, if you're just stationary, you either continue to be stationary or you begin accelerating, right? If you're currently accelerating, then you can continue accelerating, or you can take your foot off the accelerator and begin cruising, or you can hit the brake and start decelerating, right? If you're currently cruising, you can hit the accelerator and begin accelerating. You can hit the brake and begin decelerating, or you can just continue to cruise. And if you're decelerating, then you continue decelerating until you come to a stop, or you take your foot off the brake and you begin cruising, or you take your foot off the brake and hit the accelerator and begin accelerating. So this represents everything that can happen to a car, right? Does this remind you of something? What is this? Anybody else? Model? It's a Markov chain, correct? It has 4 states. And did the states make sense to you in my toy problem? How I set them up? Right, okay. So here's that. But then that's not enough information, right? So let's say that here are the distributions of the sounds the car makes when it's in different states. So when it's idling, the sound pressure level has a distribution that is around 45 dB. When it's decelerating, it's got this distribution around 60 dB. If it's cruising, it's got this distribution around 65. And if it's accelerating, it's got this distribution around centered at 70, right? So in any given state, the car is not always making the same sound. So now what you want to do is, based on what you've heard, you want to know the current state of the car so that you can work your way backwards, right? But then let's say you heard a 67 dB SPL sound. Based on listening to that sound, can you say if the car is cruising or accelerating? Can you? You can't, right? It's confusing, right? So you'd have simply knowing the current sound level is not enough to know the state of the car. So you have to consider the entire process. So here's my process again. There are 4 different distributions, one corresponding to the sounds it would make from each of the states. There's the underlying Markov chain. I'm assuming all transitions are equally likely. So if you're idling with a probability of 0.5, you continue idling. With a probability of 0.5, you begin accelerating. If you're accelerating with 1/3 probability, you go to one of these 3 states, and so on. And using this model now, you have to find your way back home. Now, exactly how will you use this model to find your way back home? I'm not going to tell you. We will figure this out in the next class. So, but this is a hidden Markov model. There's an underlying Markov chain, which is the state of the system, in our case, the state of the car. And then there's an observation, which is the sound we heard, and the distribution of the observation depends on the state. Different states have different distributions, and these might overlap, right? This is a hidden Markov model. So the model assumes that the process can be in one of a number of states at any time, and the state of the process at any time depends only on the state at the previous instant. So basically, the fact that the state that you're going to be assuming that you're currently decelerating, it doesn't matter how you came to be decelerating. It doesn't matter whether you were accelerating earlier or cruising earlier or even decelerating even earlier. All that matters is that you are currently decelerating, and that decides the future, right? And at each instant, the process generates an observation from a probability distribution that's specific to the current state. And all you get to see are the generated observations. The actual state of the process is not directly observable and must be inferred, hence the qualifier hidden. Did the setup make sense? Questions?
Yeah, so in this problem, the sound pressure that we are observing is the Y, the second level variable, and
Yes.
the state is the first variable, whether it's
Yes,
idle or
exactly.
accelerate.
Exactly,
Okay.
yes. Any other questions?
Here, does the state fall in the non-quantifiable category? Like, how do we determine whether it is or it is not?
So in this case, we are assuming that the state is quantified. It's okay. Here, in this case, it's quantized. It's a crappy toy problem. You know, when I'm saying accelerating, I haven't mentioned the actual acceleration, right? So there are four abstract states. That's all. I'm just trying to assign some semantic to the problem here. More generally, you cannot. I just created
generally
a toy.
They are quantifiable.
Generally, the state may not be quantifiable. You're really interested in the real problem you'd be interested in is saying, you know, I'm currently at 65 dB SPL. What is the SPL going to be at the next time? Right. And so when I'm thinking of it along the observation level, then I don't need to assign a meaning to the underlying state.
Okay.
Right.
Yeah.
So, but in this problem, yeah, you need to apply a meaning to the underlying state, otherwise you're not getting home. Okay. So what's an HMM? It's a probabilistic function of a Markov chain or a stochastic function of a Markov chain. It models a dynamical system. The system goes through a number of states following a Markov chain model. On arriving at any state, it generates observations according to a state-specific probability distribution. So this must have, hopefully, my little toy example conveyed this idea. So what are the components of such a model? It actually has, the hidden Markov model is, this entire model is actually a probability distribution. But it's composed of two components. The first is the underlying state transition backbone that specifies how many states there are and how they can follow one another. And the second is a set of probability distributions, one for each state, which specifies the distribution of all the vectors in that state. So just as in our toy example, right? And we're going to assume that this HMM represents a genuine process that generates observations. And how does the process generate observations? It goes through the sequence of states. The process actually follows the states according to the random nature of the underlying state and the process that governs the state. And then as it goes through the states, it's going to generate observations. So for example, if this were an HMM, this has four states. And the process would sort of follow a sequence of states through this Markov chain. So it could start off at the red state, then transition back to the red state, then transition back to the red state again, then go to the blue state, go back to the blue state, go to the black state, stay there twice more, go to the purple state, and so on. And then as it sort of progresses through the states, each time it arrives at a state, it generates an observation from the distribution associated with that state. And what you get to observe is the observation sequence that is obtained, that is the observation sequence that's generated by the process. So here's your second problem.
Is this like the Gaussian mixture example that we discussed in EM?
It is, except with one extra complexity, that the process of choosing the Gaussian is actually a Markov chain. That chooses the Gaussian is actually a Markov chain.
Okay.
Yeah. Okay. This should be easy, guys. Can you tell me which of these do you think are the various parameters that define an HMM? Anyone?
It's all of them.
All of them, right? You need to define the number of states and the transitions. You need to define the probabilities associated with all the transitions. And you need to have to specify which state you're likely to be in at the very first time instant. And you need to define the probability distribution for observations from any state. So all of them are true. So here are all the HMM parameters. The first thing is the topology of the HMM itself. How many states there are, and how you can transition from any state to any state. Here you have 3 states, and you can see that the way we've set it up, there's no way for you to go from the blue state to the red state. From the blue state, you can either go back to blue or go to green. Then you have transition probabilities. So for example, from the red state, with a probability of 0.6, you can remain in the red state. So with a probability of 0.4, you can go to the blue state, and there's 0 probability that you're going to be able to go to the green state. Similarly, from the blue state, there's 0 probability of going to the red state. There's 0.7 probability of going back to the blue state, and 0.3 of ending up at the green state. And this third row defines the probabilities for the third state. So this matrix of probabilities specifies all the transition probabilities in the Markov chain. This is also, these are also parameters of the model. And then there's a third parameter, which is often represented by pi, which is at the very first time instant that you begin observing the process, which state is the process likely to be in. So for the very first time instant, that too must be specified. And this is the initial state probability. Those are also parameters. And then the actual probability distributions associated with each of the states. The parameters of these probability distributions are also HMM parameters. Now, having specified the problem, I want to emphasize that although it looks like a 2-stage process over here, right? This entire thing is actually just a probability distribution. If you look at the complete, if you consider all possible observation sequences that this model can generate, the total probability of all of these observation sequences will be 1. So this is in fact a probability distribution. And in the nature of probability distributions, there are 3 different questions we can ask. First is, what is the probability that this process will generate a specific observation sequence? The second is, given an observation sequence, how do I decide which states the process was in generating any particular observation? This is called the state segmentation problem. And the third is, okay, I have the model. I know how I've modeled the process. I've got a whole collection of observation sequences from it. From these observation sequences, how do I learn the parameters of the model? So let's consider the First problem. What is the probability that this model, this process, will generate a specific observation sequence? Now, to evaluate this, you have to consider two things. There are two aspects in generating any observation sequence. First, the process must go through a sequence of states. Second, it must produce observations from these states. So, if this were my HMM, in order to generate any observation sequence, first it goes through a sequence of states. So if I look at the underlying Markov chain itself, that is the actual generating process, right? It begins at some state here, red in this example. And then from there, it makes an allowed transition and yet another allowed transition and so on, and keeps making all of the allowed transitions to go to proceed through a sequence of states. Now, what is the probability that the process will go through a particular sequence of states? That's this. The probability that the process will go through a specific sequence of states, S1, S2, S3, for example, red, 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 blue, blue, black, black, black over here, is the probability that it's going to be in state S1 at the very first time, times the probability that it's going to transition to S2 from S1, times the probability that it's going to transition from S3 to S2, and so on. You just multiply these probabilities through the entire sequence. So here, for example, the probability that the process is going to go through this sequence of states is the probability of being in the red state at time 1, times the probability of transitioning to red from red, times the probability of transitioning from red to red from red, times the probability of transitioning to blue from red, times the probability of transitioning to blue again, from blue this time, times the probability of transitioning to black from blue, and so on. So it's just the probability of the first state, and then subsequently you multiply the probability of transitioning from each state to the next state. So that sequence of the product of that sequence of terms gives you the probability of any specific state sequence. Did that make sense, or did I confuse you? Did that make sense, guys? Yes, no? Questions otherwise? Okay, fine. So that tells us how it goes through a state sequence, right? Now, let's say the process has gone through the state sequence. At each time, it generates an observation from the state it is in at that time. So what is the probability that given that it has gone through the state sequence, what is the probability that it will generate this specific observation sequence? So what is the probability of a specific observation sequence given a specific state sequence? Now, again, observe that when it generates any observation, it's only interested in which state it is in at that time. It has no interest. It has no dependence whatsoever on the states at other times. So the probability of generating this observation sequence is the probability of generating this observation from here times the probability of generating this observation from here times the probability of generating this observation from here, and so on. So you just multiply the probabilities of each observation from the probability distribution of the corresponding state, and you multiply this over all the observations. So the probability of the observation sequence given the state sequence is P of O1 given S1 times P of O2 given S2, and so on. Typically, these observation sequences are the state-dependent observation distributions are modeled as Gaussians or Gaussian mixtures. But that's a minor issue. The basic idea is that the probability of an observation sequence given a state sequence is the product of the probabilities of individual observations given their corresponding states. So did this equation make sense? Yes or no? Okay. And so the probability of going through a state sequence and generating a specific observation sequence is going to be, so what is the probability that this process will go through this specific state sequence and generate the specific observation sequence? That's easy enough. It's the probability of this observation sequence and the state sequence. Using Bayes' rule, that's simply the probability of the state sequence times the probability of the observation sequence given the state sequence. And the probability of the state sequence we know is just the probability of the first state times the product of all of the transition probabilities. And we know that the probability of the observation sequence given the state sequence is just the product of the probabilities of the individual observations from their states. And so now when I ask you, what is the probability of a specific observation sequence? When all I have given you is the observation sequence, I have not specified the state sequence, which means that I must marginalize out the state sequence, right? So I want to compute the joint probability of the observation sequence and every state sequence and sum over all possible state sequences. So is this equation making sense, the one on top? Okay. And if I just write it out, this is the sum over all possible state sequences of just this term, right? The product of the first probability of the first state and all of the transitions times the product of the probabilities of the individual observations from their states. I can compact it down. The problem is that when you want to compute this, this must be computed over all possible state sequences. And if I have t time steps and if I have n states in my Markov chain, how many different state sequences can I have? If I have t time steps n raised to t, right? Exponential. You're not going to be able to sum this because you have a very large number of state sequences. So we use the dynamic programming technique, which is the forward algorithm. And I'm going to use that. I'm going to illustrate the forward algorithm using a little toy HMM. Here's a simple generic HMM with 5 states. And I've chosen an HMM where the underlying Markov chain has a strict unidirectional transition structure. This is called a Baker's topology Markov chain. And the only reason I'm using this particular structure is that it's easy to illustrate. In my example, there's also a final terminating or absorbing state, which I won't necessarily use, okay? So here's how the process looks. The process now has 6 possible states for the underlying Markov chain. So it can be at any time, it could be in any of these 6 states. So I can draw this grid over here, and each of these circles represents the event that the process is in a specific state at a specific time. So this circle over here, for example, represents the event that the process was in the first state at the first time. This one over here represents the event that the process was in state 4 at time 8. So is this picture making sense? Okay. And now I can draw arrows of this kind. And this arrow is what is called a trellis. It's a graphical representation of all possible paths through the HMM to produce a given observation. So here again, the vertical axis represents the states, the horizontal axis represents time. And so here, for example, you could be in state 1 at time 1. But from state 1, you can either continue in state 1 by following the self transition, or you can go to state 2 because it's possible to transit from state 1 to state 2. So ignore the vertical lines over here. What you'll observe is that this collection of arrows is simply basically this structure to the left, unrolled over time. And so in this case, any node over here represents the event that this observation was generated from this state. And this entire structure, this trellis, represents the various state sequences that the Markov chain could have followed while generating this observation sequence. So, for example, this path over here represents the event that the process went to state 1 at time 1 and generated this first observation, and then to state 2 at time 2 and generated this observation, and then state 3 at time 3 and generated this observation, and stayed at state 3 to generate this one, went to state 4 to generate this one, stayed at 4 to generate this one, and so on. So is this picture making sense? Okay. So now the probability of a particular path. Now a path over here represents a combination of a state sequence and an observation sequence. So the probability of any particular path through this trellis is going to be the probability of the state sequence times the probability of the observation sequence given the state sequence. So that's going to be P of S0 times P of O0 given S0 times P of S1 given S0 times P of O1 given S1, and so on. So that's given by this equation here. Is this equation making sense? Overall, yes or no? Easy, okay? So now let's consider this sub portion of the trellis, right? If I look at, again, ignore the vertical lines, though they're just there to help me with my pictures. If I look at all of the paths in this sub portion of the trellis, they're all ending here, right? So this subgraph represents every possible state sequence that the process could have followed that ended in this state S at time t, while also generating this observation sequence. Does that make sense? What's the interpretation? Rest of you guys, anyone? Is there any doubt about what this is? We're going to use it so in the next 3 classes, so it's important. Some of you have, okay. Raise your hands if it makes sense. I will wait. If it does not, please ask me where I lost you. Okay. So again, this term is going to be represented as alpha ST. Alpha ST is the event that the process somehow ends up in state S at time t and generates all of these observations, O0 through OT, right? Now, how can I compute this? So alpha ST is the total probability of all state sequences that end at state S at time t, and while generating all observations until time t, okay? So it's alpha ST is P of x1 through xt, and state at time t is S. And this can, you can see where this is going. This can be recursively computed. Now, alpha ST is the probability that the process ends at state S at time t. What is it? You can arrive here either from this state by being at this state at time t minus 1 and transitioning here, or by being at this state at time t minus 1 and transitioning here, or being at this state and transitioning here, right? So the probability of being in this state at time t minus 1 is the probability of all state sequences that ended in this state and all observations until here. So that's going to be alpha ST minus 1, right? This is going to be whatever. Let me call this 1, 2, 3. So this is alpha 3t minus 1, right? This is similarly, the probability of being in this state at time t minus 1 is alpha 2t minus 1. This is alpha 1t minus 1. So the probability of being in this state at time t is alpha 3t minus 1 times the probability of transitioning from there to here, plus the probability of being here at time t-1 times the probability of transitioning from there to here, plus the probability of being here at t-1 times the probability of transitioning from there to here. But all that does is to bring you to this state. From this state, to complete the entire description, you also have to generate the tth observation. So to that entire term, you must now multiply p of xt, the tth observation given s. So what this means is that the alpha at any state is the sum over all of the parents in this trellis of that. The alpha of any state at any time is the sum over all of the parents in the trellis of the node that represents st, and the sum is of the product of the alpha at the parent times the transition probability from the parent to the current state. So this is the sum. And once you take the sum, the final sum is multiplied by the probability of generating the tth observation from the state itself. So I'm not sure if I conveyed the idea, but is this making sense? I mean, it's a simple enough idea, right? It's just simple DP. Right, and depending on you guys understanding the DP and not on my words, which are very confusing to me. But okay, so given that, it's easy, right? This is DP, right? I can start off by computing my alphas at the first time instant. Then the alpha at the first time instant is simply going to be the initial state probability of the state times the probability of the first observation given the state for all of these states. And then given these alphas, you can use the alphas at each time to compute the alpha at the next time and the next time and the next time till you get to the final observation. So once you've got to the final observation and the sequence, you know that for the final observation, you must be at one of these states. So the total probability of the observation sequence is simply going to be the sum of the alphas at all of these states. Basically, it's the probability of the observation sequence in this state plus the probability of the observation sequence in this state and 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 so on. So the total probability of the observation sequence is the sum of the alphas at the final time. That makes sense? Yes or no? There's some doubts. I'll wait. Any doubts, guys? Okay.
Just a quick question about this.
Yeah.
So it seems that why would the probability of the sum or the total probability not be 1? Because it seems like the sum would encapsulate all possible observation and state sequences.
No, so because observe this, it's not going to be 1. It's at each point you have p of xt given s, right? This is a specific observation, correct?
Yeah.
So you're always going to have a specific observation. How many different observations? So, correct?
Yeah.
If you consider all possible observation sequences, then it would be 1.
That makes sense. Okay.
Right? So, over here in this formula, okay, no, you don't. This is just the alpha. The alpha already includes the current state or the latest observation, right? You can tell? So alpha st over here is going to be the probability of all observations until here and being in the state. Similarly, the alpha for this state is the probability of all observations and being in the state. So if I sum out the states, I'm just going to end up with the probability of all observations. Or the observation sequence. So you tabulate which one here. So no, this is xt because I have arrived at state S. And then from state S, I must generate the tth observation. Xt minus 1 is already factored into the previous alphas, right? Yeah. Okay, all three. Okay, guys. Anybody want to answer the first question?
Third one.
The third one. Second one? Second question? True. Okay. Thank you. Right. Any questions so far? Any questions, folks? Okay. So what we have seen so far is how we can compute the probability of an observation sequence for the HMM, right? And we agree that it's not going to be 1. It's going to be the probability of the observation sequence. If you sum it over all possible observation sequences, or if you integrate it over all possible observation sequences, what will that value be? Anyone? That's going to be 1, right? So the HMM is a probability distribution. It's a very complicated probability distribution, but it's a probability distribution over time series. Make sense? Okay. So now here's the second problem. This is more interesting to us for various reasons, which you won't see immediately, but maybe in 2 classes from now. You're given only a sequence of observations. How do we determine which sequence of states was followed in producing this sequence of observations? So again, for this, let's go back and look at the HMM as a generator. The HMM, the process first goes through a sequence of states, and at each time it draws an observation from the distribution associated with that state. Except you're only given the observation sequence. And based on this observation sequence, you have to determine the state sequence. Have we seen a problem like this recently? Anyone? Have we seen a problem like this recently? The Daironi example. Guys.
Kidnapping problem.
Pardon me? The kidnapping problem, right? It wasn't that. So you just got to hear the sequence of sounds and you had to determine the sequence of states. Does that ring a bell? Yes, no? Humor me. Just give me a yes. Yes, thank you. All right. So keep your eyes open, right? The kidnapper will come back. But anyway, so what we know is that there isn't a unique sequence of states that can generate a given observation. If you'll remember my kidnapping problem, we saw that there were some sound levels that could have come from multiple states, right? So there are many different state sequences that are capable of producing any given observation. So we want to identify the specific state sequence that produced it, but then we can't know which one it was actually, right? So instead, we will identify the most probable state sequence. So the state sequence for which the probability of going through that sequence and generating the observation sequence is maximum. So you're going to determine the state sequence S1, S2, S3 such that the joint probability of the observations and the state sequence is maximum. What we actually want is the state sequence such that P of state sequence given observation sequence is maximum, but that's exactly the same as finding the state sequence for which the probability of the state sequence and the observation sequence is maximum. So this is what we're going to try to do. Did this make sense? Okay. So again, we want to find the state sequence such that P of S1, S2, S3 given O1, O2, O3 is maximum. But instead of finding that, we're just going to find the state sequence for which P of S1, S2, S3 and O1, O2, O3 is maximum, because by Bayes' rule, both are equivalent, right? So we want to find, you're given the observation sequence. You want to find the state sequence for which this term is maximum. And in theory, if you were being naive, you could just plug in every possible state sequence out here, compute the joint probability, and can compute the joint probability using this formula that we've seen earlier, and then find the state sequence for which this term was maximum. Again, this is not going to be feasible because there are an exponentially large number of state sequences, right? So it's exponential in the length of the sequence. And so we're going to use dynamic programming, right? And to use dynamic in performing this dynamic programming, we observe something interesting. First, the joint probability of the observation sequence and the state sequence is the probability of the state sequence, which is shown by this red underlined portion of the equation, times the probability of the observation sequence given the state sequence, which is shown by this portion of the equation. Now I can restate this by grouping things together. I can group this first P of O1 given S1 with P of S1. That's my first term. I can group P of O2 given S2 with P of S2 given S1, and so on. So I have grouped these things together. Now, what is this grouping really doing? If you go back over here, this was the process by which the HMM generated an observation sequence, right? It went through a state sequence, and as it progressed through the state sequence from each state, it generated an observation. So we are trying to find the state sequence for which the overall probability of this process is maximized. And we can sort of decompose this into the product of the probabilities of individual columns, except that we have to consider every arrow in this figure. And so if you look at any particular column, you have to consider the arrow going into the dot, into the state, and the generation of the observation from that state. And so this term over here, that's enclosed in an ellipse, captures this probability. The P of S2 given S1 is the probability of this edge, and P of O2 given S2 is the probability of this column, which shows the event of this observation being generated from this state. So did this decomposition make sense? Yes, no. Right? Easy enough, right? Any questions? No. And so we can use this simple observation to come up with our dynamic programming algorithm, right? And the dynamic programming algorithm is based on the simple observation. The probability of a state sequence that ends with Sx and Sy at time t and produces all observations until time t can be basically written as so basically the question I'm asking is, what is the probability of a state sequence that ends at Sx over here and Sy over here while generating all of these observations? That is simply the probability of the state sequence that ends at Sx while generating all of these observations times the probability of transitioning from Sx to Sy times the probability of generating this particular observation from here. Does that make sense? Yes or no? Right, okay. So this ugly equation over here, which I won't try to decipher myself, it's better explained with this picture, is basically asks, what is the probability that I'm going to end up with, that I'm going to generate all of these observations and be in the red state here and the blue state here. That's going to be the probability of being in the red state here and generating all of these guys times the probability of going to blue from red and generating this one, right? So the best state sequence, what is the most likely state sequence that ended with the red state and the blue state? Because extending the state sequence is only factoring any additional terms. It's not changing anything in the past, right? So the best state sequence, the most probable state sequence that ended at the red state here and then transitioned to the blue state here while generating all these observations is simply the extension of the most probable state sequence that ended here by the blue state. So the most probable state sequence which ended with red and blue states is simply exactly the same as the most probable state sequence that ended at the red state and was then extended to the blue state. Did that make sense? Or did I confuse you? Okay. All right. And so basically, here's what we're saying. The probability of the state sequence Sx, Sy ending at time t and producing observations until OT is simply going to be the product of the state sequence within the purple box times this extension, right? So the probability of the most probable state sequence ending with the red and blue is going to be the most probable state sequence ending with red over here, or rather the probability of the most probable state sequence ending with red and blue is going to be the probability of the most probable state sequence ending at red times the probability of transitioning from red to blue times the probability of this tth observation. That's it, okay? And so using this, going back to my trellis, I can ask myself, so basically what that says is that I can assign a change in score due to extending a state sequence from, say, Sx to Sy, and that's going to be simply the probability of the state sequence that ended at Sx times the probability of transitioning from Sx to Sy times the probability of generating the tth observation from Sy, right? And so the cost of extending the state sequence from here to here, or the amount by which the probability changes when you extend the state sequence from here to here, is simply going to be this transition probability times the probability of the tth observation from this state. Simple, right? So now, the best path to Sy through Sx is definitely going to be the best path to Sx extended to Sy. So the probability of the best path that goes from Sx to Sy is the probability of the best path to Sx times this transition probability times the probability of generating the tth observation from Sy, right? And so if I look at the best overall path to Sy, now in this case, there are only 3 incoming edges to Sy. So if I want the best overall path, if I want to find out which is the probability of the most likely path that ended up at Sy, the most likely path that ended up at Sy had to have come through one of these 3 things. So to find out which of these 3 was the most probable, all I have to do is to say, what is the probability of this path? What is the probability of this path? What is the probability of this path? I can compare all 3 and just pick the best. And the probability of the best path to this node, let's assume it's known. If I know the probability of the best path to this node, then multiplying the probability of the best path to this node by this transition probability, and then comparing it to the probability of the best path to this node multiplied by this transition probability, and the probability of the best path to this node multiplied by this transition probability. If I just compare the 3 and pick the largest, then I know which is the best overall path coming to this node. And so the probability of the best overall path coming to this node is simply going to be the probability of the best path coming in here times the probability of the tth observation from this node itself. This is, again, just straight up dp, right? I know I sort of made it sound more complex than it is, but I'm assuming that most of you just know this stuff. And if you don't, you can ask, but did this make sense? Over here. Right. Anybody to whom it didn't make sense? I'm assuming not, right? So if I want to find out what is the best path, I'm missing some slides over here. I'm not sure why. Yeah, here it is, right? So this algorithm, the simple algorithm is just called the Viterbi algorithm in the literature after A.J. Viterbi, who invented this algorithm for decoding error correction codes, actually. So here's how I could find the best path through my state sequence. In this case, I'm using this little toy example. I'm only allowed to be in this state at time 1 because it's a strictly left to right Markov chain. So B1 of 1, this is shorthand for me, is the probability of the first observation being generated from state 1, right? State S1. So at the very first time instant, the first observation must be from this state. So the best path to this state is just the state itself, right? And its probability is the initial state probability of the state times the probability of the first observation from the state. I can compute it for all of the states, except that in my example, I'm assuming that you're not allowed to begin at any of these states. And so for the best path probability to the rest of the states would be 0. Then at the next time, for having assigned a best path probability to all of these states, I can go up to the next time and compute the best path probability to all of these states. And in so doing, for each state, I'm also going to know the best predecessor. So I can keep track of the best predecessor and find the best path probability to the state. So, again, you're just finding the max over all parents of the node of the product of the best path probability to the parent times the transition probability, right? And then you're factoring in the observation probability itself. So you can keep doing this you'd find the best path probabilities to all states at the second time, and then the third time, and the fourth time, and so on. And at each time, at each state, you're going to keep track of 2 things: the best path probability to the state and the best predecessor. So having done that, now at the final time instant, let's just say, as in my example, you're sort of decreed that the final observation must be from the state. It's an absorbing state. Then I can just find out the best path probability to this absorbing state, find its best predecessor, find its best parent, and track my way back and find the most likely overall state sequence through the HMM. So the best state sequence over here is the estimate, or the most likely state sequence over here is the estimate of the state sequence followed in generating an observation. So I know this was kind of confusing, but let's have a poll. I'll stop after this poll. Okay. First question, guys, what's the answer? What's the answer to the first question, folks? Second one, also true, right? Easy enough. Thank you. I know this looked I made it sound more tedious than it is. It's actually a very simple algorithm. And I'm sort of going to assume that you understand it in the next class, because in the next class, we'll begin talking about training HMM parameters. And then subsequently, we're going to just extend these ideas to compose Kalman filters. We'll stop right here and I'll take any questions. Any questions? I'm assuming not. Thank you very much. And there's no class on Thursday. So I'll see you next week on Zoom.